Hey, want to see a magic trick? Major upgrade, huh? All right, let's continue with our discussion of 1.6. Here we're going to be looking at some examples I found in the text, some that are not in the text. What we're really trying to do here is understand how we might use algebra to solve limits algebraically. Look at this first one right here. The limit as x approaches negative 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. You could use the limit laws at this point to solve this problem. But fundamentally, what are you doing when using the limit laws? Really just one thing. You're plugging in the value that x is approaching into f of x. So as x approaches negative 2 means plug negative 2 into each of these x values and see if this thing just solves out, and it does, right? If we plug in negative 2, we get negative 8 plus 8 minus 1 over 5 plus 6, which is negative 1 over 11. Done. Nothing to it. If we were to use the limit laws, what limit laws would we be using? Well, we could take the limit of a quotient is actually a quotient of limit, so you could put a limit up here and a limit down here. Then this limit of the numerator would be of a sum and of a difference, so you can break it up into the limit of a sum becomes a sum of limits, and the limit of a difference becomes a difference of limits. Same thing down here, you can go with difference of limits. You could pull out this constant 2 out of that limit, this constant 3 out of this limit. You could certainly use your limit laws. The limit as x approaches negative 2 of 5, what would that be? Well, that's as x approaches negative 2, 5 approaches 5. See, so you could use all those limit laws, but really, what are they fundamentally coming down to? They're coming down to plug in what x is approaching into f of x and solve for what f of x is approaching. All right, now we get these next few cases, which are all cases of, do you remember the term? Indeterminate form. What does indeterminate form mean again? It means I don't know yet. I got to do more work. Got to do some algebra. The algebra we're doing here is not limit law algebra. It's the kind of algebra you've done on algebra problems for years now. Watch. The limit as x approaches 3 of x squared minus 9 over x minus 3. If you plug in 3, you get 0 for 0, which is a what type of form? An indeterminate form, that's right, which means what again? I don't know yet, so I got to do more work. So I said the limit as x approaches 3 of this guy equals the limit as x approaches 3 of that guy. What did I do? I noticed this was a difference of perfect squares. I know it'll factor. And the beautiful thing about the factoring, of course, is that x minus 3 over x minus 3 equals 1. 1 times x plus 3 is x plus 3. So now I have the limit as x approaches 3 of x plus 3. Just plug in 3 and you get 6. Done. This is a case where we had an indeterminate form. I didn't know yet. I did some algebraic trickery and boom, I've got what f of x is approaching. As x approaches 3, f of x approaches 6. Here's another such example. The limit as t approaches 0 of the square roots of t squared minus 9 plus 9 minus 3 over t squared. What's the problem? If I plug in 0 up here, I get square roots of 9, which is 3, minus 3, which is 0, and I get 0 squared, which is 0. 0 over 0 is a indeterminate form, which means I don't know yet. I got to do some algebra. What algebra can I do? Well, you've seen this before. Something like this in all your algebra work over the years. And when I'm going to handle a situation like this and I want to get rid of the square root sign, what do? Yeah, I multiply its conjugate, right? And you can only multiply a number by 1 in order to keep its identity. So multiply it in the form of square roots of t squared plus 9 plus 3 over square roots of t squared plus 9 plus 3. When I do that, I'm going to multiply through. These will cancel, and these will produce something. Basically a difference of perfect squares, right? And so the square roots of t squared plus 9 squared is t squared plus 9. And the minus 3 times the 3 is minus 9. And the middle parts cancel out. The bottom, we just leave them as they are. The beautiful thing here is, look, 9 minus 9 is 0, so you lose your t squared in the top. T squared divided by t squared is 1, leaving you 1 over this bad boy. At this point, what have I achieved? I've achieved a situation where I can plug the value t is approaching into f of t and get out what f of t is approaching. Watch, if I plug in 0, I get 1 over 3 plus 3, which is 1/6. Done. This problem up here, not an indeterminate form. I plugged in the x values approaching, got what f of x is approaching. These two problems, they both came up with 0 over 0, which is indeterminate form. I don't know, and so I did more work. Algebra. That's it. Look at this problem. Very similar. Limit as h approaches 0 of 3 plus h squared minus 9 over h. Well, what if I plug in 0? What do I get? Clearly 0 over 0. What am I going to do? Well, this right here is a nice, beautiful quadratic in standard form. I don't have to leave it in standard form. I can bring it to general form by just doing what? Yeah. So, 3 squared plus 6h plus h squared minus 9 over h. Hey, look again, 9 minus 9, that cancels out, leaves you with this. You've noticed there's a common factor of h in the numerator. Factor that out. Now, h divided by h is 1. 1 times 6 plus h is 6 plus h. The limit is h approaches 0. 6 plus h, just plug in 0. What do you get? 6. In each of these cases, indeterminate form, I don't know yet, and so I go ahead and do some algebra so that I can plug in what x is approaching and find out what f of x is approaching. Basically, evaluate the limit. All right. Let's look at these bottom four right here. The limit as x approaches pi of x cubed. X is approaching a value. What do I do with that value? I plug it into f of x, and what do I get? Pi cubed. Is that an answer? Of course, pi cubed is just a number. As x approaches pi, f of x approaches pi cubed. No problem. How about this? The limit as x approaches pi of 7. Remember, this is a constant linear function. No matter what we have x approaching, x can approach pi from both directions. 7 is going to remain 7 with a slope of 0, constant linear function. So as x approaches pi, 7 approaches 7. Don't want you to forget that. How about this one over here? The limit as x approaches pi of e. E is just a number, it's just a constant. So no, it doesn't matter what x is approaching. X approaches 1, 2, 3, it doesn't really matter. X approaches pi, e is going to approach e. All right, how about this? The limit as x approaches 3 pi over 2 of sine of x. What do? I just plug in this value in for x, and I get sine of 3 pi over 2, which is what? -1. All right, to recap, these examples, I'm just plugging in the x value I'm approaching and solving. That's the case down here. These examples, I wind up with a 0 over 0 situation. Whenever I wind up with 0 over 0, infinity over infinity, negative infinity over infinity, I have an indeterminate form. I don't know yet, so I do some algebra to get to a place where I can plug in the value of x that's being approached and find out what f of x is approaching.
What is it again? Welcome back to school. My dad is your teacher.
Well, thank you, Evangeline. Thank you, Abigail, and welcome back to students. All right, we pick up with limits, but this time we're looking at a particular class of functions called piecewise defined functions. Now, hopefully you finally figured out what they are, how they work, because we're going to be looking at them today when we look at limits, and this is very frequent. Look at this first function. I just made it up. It's really a combination of a bunch of functions. F is the name of the function. What type of function is? A piecewise function. It consists of how many pieces? 3 pieces. Piece 1 is a linear function, slope of 1, y-intercept of 1. Second function is a constant function or a constant linear function. That's a function that looks like this, whose slope is 0. F of x equals negative 1.5, just a line. Okay, and then the third function is what type of function? Cosine function. F of x equals cos x. Now look, you use the first function, the linear function, over this portion of the domain when x is less than 0. So f of x equals x plus 1, that's that function right there, when x is less than 0. Hence an open hole and an arrow on this end. F of x equals negative 1.5. Now that would be this line right here, wouldn't it? But where are you going to use that function? Only where x equals 0. So just right there at that dot. Do you see it? Okay, and then finally, f of x equals cosine of x, where x is greater than 0. Can you see the cosine function happening?
Yes.
Notice it's an open dot here and an arrow. Thank you. All right, so you know how to graph this guy. You know where the zeros are happening. That's at negative 1 for this guy. This zeros are happening here at pi over 2 and 3 pi over 2. You know what this thing looks like. Now if I ask you this question, what is the limit as x approaches 0 from both directions of f of x? What would it be? Well, as x approaches 0 from both directions, clearly what is f of x approaching? Follow x comma y. Where are they going to? Well, it looks like y is going up to 1. And that's the answer. You effectively have to look at the left-hand limit and the right-hand limit and make sure they're the same. The left-hand limit, which function would I use for the left-hand limit? As x approaches 0 from the left. Clearly this one. This is where x is less than 0. So I'm going to use this function, f of x equals x plus 1. The limit as x approaches 0 from the left of x plus 1. What do? How do I handle this algebraically? Just plug it in. 0 into here and you get 1. As x approaches 0, f of x approaches 1. How about the right-hand limit? Well, for the right-hand limit, as x approaches 0 from the right, I've got to use this function, don't I? Yes, of course, because x is greater than 0. So limit as x approaches 0 from the right of cosine of x equals, well, how do you handle this? You plug in 0 into cosine function. Cosine of 0 is 1. You know that. If the left-hand limit and the right-hand limit are both equal to 1, then the two-side limit equals 1. Good. Now, a completely irrelevant question to the limit is this question. What is f of 0? What is f of 0? What does that mean? It means stick 0 into the f function and see what you get out. Well, if I stuck 0 into the f function, which part am I sticking it into? 1, 2, or 3? Clearly part 2. Why? Because x equals 0 is only in the domain of this part of the function. So if I plug in anything into the constant linear function f of x equals 1.5, whether it's f of 0, f of pig, f of dog, it doesn't matter what it is, f of 0, what's going to come out? Negative 1.5. So f of 0 is negative 1.5, completely unrelated to the limit. I hope this is making sense to you. I hope piecewise functions make sense to you. If not, you really need to reach out to me and get some, it's like video chat time. Come to my video student hours. You just really need to understand piecewise functions. All right, here we go. Function number 2, what's the name of it? G. What type of function is it? Piecewise defined function. The first piece is a linear function. The second function is a constant function. Slope of 0, and where's it at? It's at y equals pi. Pi is just a number, approximately 3.14, you know that. Now look at it very carefully how it's broken up. The linear function over what portion of the domain? All real numbers except for one independent value. What is that? X equals 1. For that independent value, x equals 1, use the constant linear function, g of x equals pi. Okay, look at the function. Is that what you imagine in your head? It should be. For all intents and purposes, except for this one point here, the whole function looks like this. G of x equals x plus 1. You know what that looks like. A slope of 1 goes through y-intercept of 1. Except we got to leave out x is equal to 1. That's not part of this function. So leave a hole where x equals 1. Then fill it in with this guy. G of x equals pi when x equals 1. So when x equals 1, g equals pi. Pi is just above 3.14. There's that point. Do you see it? Do you see it's a function? Do you see it passes the vertical line test, that it's defined for all real numbers now? Do you see it? Good, I hope you do. The limit as x approaches 1 from both directions is clearly what?
2. It's completely irrelevant where the point is. If we were to do this algebraically, because you can't draw a graph for every function. If you do this algebraically, you'd have to say here's the left-hand limit as x approaches 1 from the left of what? Which function? This guy or this guy? The top guy. Why? Because when x is less than 1, that's included in this portion of the domain. Plug in 1, you get 2. How about the right-hand limit? Might you use the top piece or the second piece? Still the top piece. Why? Because when x is greater than 1, that's this. X is not equal to 1. The only time you'd ever use this function is when x equals 1, and that's not what we're saying. So again, plug in 1, you get 2. If the right-hand limit and the left-hand limit are the same, then the function equals 2. All right. Completely unrelated question to the limit again is, what is f of 1? What does that mean? Or actually it should be what? It should say, well, I don't have a pen, but it should say g of 1. If I put g of 1 means what? Stick 1 into the g function. What will come out? Pi. Right? So 1 comma 3.14, 1 comma pi. G of 1 equals pi. All right, now we move on. Here's a third function. What type of function is it? Piecewise defined function. What's its name? H. Now, if it was just written like this, h of x equals the absolute value of x, and I asked you what the shape of the graph is, you'd probably all tell me it's the V that goes through the origin, and you'd be correct. But I want you to assume you kind of didn't know that. Whenever you see an absolute value function, because they could be really complex if they have an absolute value in there, you have to decompose it into its pieces. It is fundamentally a piecewise defined function. So make sure you can decompose absolute value into its pieces. Absolute value of x. What does that really look like? Well, it really looks like negative x, the linear function h of x equals negative x when x is less than 0. It's h of x equals positive x when x is greater than 0. Thanks, babes. All right, that was my daughter telling me that there was a marker, in fact, there. All right, let's try drawing this function then. You know what it looks like. When h of x equals negative x when x is less than 0. What is h of x equal negative x? That's a linear function with a slope of negative 1 that goes through the origin. But we only go up until x is less than 0. So whole, and then this guy. How about h of x is equal to 0? What kind of function is that? A constant linear function. It's basically the x-axis. When x is equal to 0. So we don't draw the whole thing, only where x equals 0. So that's this point, 0 comma 0. And then h of x equals x. What's that? A linear function with a slope of 1 when x is greater than 0. What does that look like? Only here when x is greater than 0. There'd be an open hole there, but this guy closed the hole. This is the piecewise defined function that really is being explained by absolute value of x. Whenever you see h of x equals absolute value of x, I want you to think, aha, that's a nickname. That's a short way of saying this. And whenever you see this function like this, if you're going to solve it algebraically, you need to make it first into a piecewise defined function. Remember, we're not solving it graphically. Algebraically is what we're really doing here. So let's look at this thing. As x approaches 0 from both directions, what does h of x seem to be approaching? Well, clearly h of x, your y values are approaching what? 0. So that's going to be the two-sided limit. The limit as x approaches 0 from the left. Algebraically speaking, which piece am I going to use if x is approaching 0 from the left? The first piece, when x is less than 0. So, as x approaches 0 from the left, h of x is what? Negative x. So plug in 0, what do you get? Negative 0, which equals 0. As limit as x approaches 0 from the right, well, which piece are you going to use? Clearly this piece, h of x equals x, which is this guy right here. Limit as x approaches 0 from the right of x. What do? You take 0, you plug it in for x, and out comes 0. If the left-hand limit and the right-hand limit are both 0, the two-sided limit equals 0. Very good. Finally, the irrelevant question to this topic, and I hope you're seeing that now, is what is f evaluated at 0? Or what is f of 0? What does this mean? Plug 0 into the f function. Well, which piece do you plug? Oh, this is not F again. This is, once again, H. Okay. What is H of 0? Well, which piece am I going to plug it into? 1, 2, or 3? Second piece. That's the portion of the domain that's happening here. And what is H of 0 going to be? 0. It's always going to be 0 for that particular function. Okay. So what do you need to see here? 3 things. First thing you need to see is that you need to be able to handle these things called piecewise defined functions. Sometimes they're spelled out for you. You have to be able to kind of draw them and think them through. Other times they're spelled out for you. You got to kind of draw them and think them through. And other times they're not drawn for you. And you have to kind of rewrite them in the long form, which is the piecewise defined form. Once you've done that, you need to evaluate the two-sided limits. When you evaluate a two-sided limit, kind of at these interesting points, clearly here the interesting point is x equals 0. That's why you're taking the limit as x approaches 0. Here clearly the interesting point is x equals 1, so the limit as x approaches 1. Here clearly x equals 0, so the limit as x approaches 0 we're going to take. How do you take these two-sided limits? You make sure you take a left-hand limit and then a right-hand limit. A left-hand limit, then a right-hand limit. A left-hand limit, then a right-hand limit. And it's very important that what you do when you take these left-hand limits or right-hand limits algebraically is use the right piece. For this guy, the left-hand piece is this piece, and the right-hand piece is this piece. For this guy, the left-hand piece is the top one. The right-hand piece is also the top one. You completely ignore the second piece in this guy. And then finally, for the third function, h, the left-hand limit, you're going to use this piece, and the right-hand limit, you're going to use that piece. All right. Also, you should absolutely know what f of 0 is, g of 1 is, and h of 0 is. Just plug it into the function. But that's irrelevant for limits. Remember, limits are as you're infinitely close to a point, not the actual point. I hope that clarifies things. Thank you.